The WERI seminar series, number 2 in this case. So today we have two guest presenters. We have Dr. Natalie Collar, who's a senior hydrologist with Wright Water Engineers out of Denver. Natalie has a PhD in civil and environmental engineering from Colorado School of Mines. And then also we have joining us Dr. Andrew Earles, who has also a PhD in civil and environmental engineering from University of Virginia, and who's a vice president of water resources at Wright Water Engineers. So with that, I'll let you guys take it over and introduce yourself with additional info if you prefer.
Great. Thank you so much, Tim. I really appreciate the great introduction, and thanks to all of you in the conference rooms and also online who are attending today. Natalie and I really appreciate the opportunity to be a part of this seminar series. And we work for a company called Wright Water Engineers. We are based in Denver, Colorado. We have a couple of offices on the west slope of Colorado, and but we do work really all around the country, probably mostly in the Western United States. And over the past 20 years or so, or 25 years or so, we've developed a real practice in looking at post-fire hydrologic hazards. And that's what Natalie and I want to talk to you about today. And we want to give you an example, talk a little bit about a program that we've been a part of developing here in Colorado that is called Wildfire Ready Watersheds. And the intent of the Wildfire Ready Watersheds program is to have awareness of the potential hazards that a wildfire can produce related to hydrology, and to figure out what we can do in advance to mitigate those hazards or avoid them or have better warning. So it's really a program that's about proactive planning for these types of hazards, which all of us that live in the Western United States are going to face at some point in our communities and in the future, unless we're able to figure out a way to stop fires, which is quite a tall order. Before we move ahead, though, I wanted to mention, this is a big program that was created for the state of Colorado. We did this work working with the Colorado Water Conservation Board. That's kind of our water management agency in Colorado. They manage flooding, they manage our water rights system. So they were really the proponent for a lot of this. And we worked closely with some other partners. A company, Olson Associates, was really the prime on this contract. A guy named Jeff Sickles, who had founded a company named Ingenuity and now works with Olson, really led the team. And we've worked with other partners like Watershed, Water and Sciences, and Peak Flow, and others on these various projects, because there are a lot of different types of things we have to evaluate. So it's almost always a multidisciplinary effort. Next slide. I want to just give a quick overview and outline of the seminar. We're going to start by talking a little bit. Natalie, I believe, Natalie's going to take these slides. We're going to talk a little bit about pre-fire hydrologic hazard planning in Idaho. I will then give a little bit of an overview of Colorado's Wildfire Ready program at a high level. Natalie is then going to give a case study of a Wildfire Ready Action Plan, which is really the product or the end result of what this WRW does. And then I will wrap up the presentation by talking about resources for additional information that may be useful to you. So Natalie, next.
Great. So we're talking to people in Idaho, and we live in Colorado, admittedly. And I did a little bit of digging, but I'll try not to misstate or pretend like I'm an expert in what your state is doing to look at Idaho hazards in a pre-fire context. But just looking at your state, you're in the Western US, just looking at MTBS or monitoring trends in burn severity mapped wildfire perimeters, you have a lot going on in terms of wildfire. And I bet most people on the seminar today are working in some aspect of fire, whether it's the acute wildfire activity or hydrologically driven hazards post-fire. But just kind of as a proxy of what's happening with post-fire hazards, we can look at trends in your stats as mapped by MTBS. So MTBS they have a nice web interactive tool. Again, I bet most people here have downloaded burn severity gridded data from MTBS. And the trigger for MTBS to map a wildfire in the Western US is the fire event has to consume at least 1,000 acres. And I think it's 500 acres in the Eastern US. So since June 1984, there's been just over 1,700 MTBS mapped fires in your state. And 600 of those have occurred since 2010 and 139 since 2020. So I didn't plot trajectories here, but I think it's common knowledge that fire activity is increasing, at least relative to June 1984. There's been some work by Brendan Murphy's group to say, you know, we put satellites up in the air in June 1984, so sure, fire activity has increased relative to 1984, but fire activity relative to pre-colonial times, we actually have less acres burned today than we did maybe back 200 years, 500 years ago, and then looking back from there. But the real thing to think about is not just acres burned, but acres burned at moderate to high severity. So what is that? How severe is the fire activity, and what are the repercussions on soil hydraulic properties and vegetation? So from that standpoint, I'm not showing those stats here, but we are seeing more area burned at moderate to high severity, and that has real repercussions for hydrologic impacts post-fire. So I'm going to talk in a few slides about what is going into our hazard planning in Colorado. But just thinking about your state really quickly, what we've done in Colorado is looked at, okay, where is there severe wildfire activity? So where do we have high density fuels? And how does that overlap with assets in the landscape that we really care about protecting from those hazards? That might be water supply infrastructure, say intakes. It could also be utility lines. Where do people live and recreate? And just taking a quick glance, there should be no surprise here. But what kind of data can we use to think about where in Idaho do we have intersections of severe wildfire activity and population? So I just took a quick buildings, what is this? It's a rasterized layer that I then summed to be buildings per acre to normalize by area, and each HUC 12 in Idaho. So you can start seeing darker green colors are where more population centers are. This is where Boise is located-ish. And it's this type of analyses that's the building blocks for wildfire ready action plans. Where do we have high density of infrastructure or people, and where do we have severe wildfire activity? And therefore, where will we have flash flooding, debris flows, et cetera, that actually impact our workings in those areas. So the other thing I want to mention in terms of your state is I published a paper back in 2021, and I was looking at evapotranspiration changes after wildfire, because ET is one of the main losses of water in the hydrologic cycle. So where we saw big changes in ET, specifically reductions in evapotranspiration after fire, you can assume that there's been a major upset in hydrologic cycling. You know, where is water being distributed in the landscape? So in figure D down here, we had Idaho. Idaho is just right here. Sorry, this is figure D. And the point is, Idaho was seeing pretty big changes in evapotranspiration after fire. I had a table, this is in the supplementary information of this journal article. And the only thing I want you to take away from this busy table are here. Idaho is the state with the largest average burn area sizes per event. So Idaho has really large fire perimeters, larger even than California and Nevada. I think those are second and third in line. And perhaps most importantly, this column here is showing the percent change in evapotranspiration after fire in the first post-fire year, normalized by the amount of precip the area got on a water year cycle. And Idaho has major reductions in evapotranspiration after wildfire. So that has implications for post-fire hydrologic processes. You have a lot more water all of a sudden available to run off, contribute to flash flooding. It also has major implications for vegetation health and recovery, and for water supply. And that's all I'm going to say about the science of what's happening in Idaho and post-fire hazards, because we're going to jump to Colorado now. But as far as from a programmatic perspective, I did, again, do a little bit of digging to understand what, from a programmatic level, Idaho is doing to look at post-fire hydrologic hazards in a pre-fire context. And I did not see any equivalent program to the Colorado's Wildfire Ready Watersheds program that Andrew and I are going to talk about today. You do, of course, have bear planning and the USGS debris flow hazard modeling and post-fire scenarios. There are certainly several strong universities, and we're talking to many students and faculty today from those universities that are looking rigorously. But from a state perspective, having a really intentional concerted program to evaluate post-fire hazards, we haven't seen that yet in your state, and therefore we think that there is a lot to gain from really describing what we're doing here in Colorado. Andrew, I will hand it over to you.
Thanks, Natalie. And I will spend a little time now telling you about the Wildfire Ready Watersheds program. And, like Natalie said, a lot of states do have a lot of different various programs with fire. And for example, in California, they have the work teams with NRCS that go out after fires, and of course, bear teams. But, all of those are after the fire. And really what the motivation behind this program was really to figure out what can we do before a fire, what can we plan on, and what can we do before a fire. Because once you have a fire, it's people are scrambling around. It's hard to get things done in a very short period of time. So having a long lead for planning what you're going to do and knowing where the hazards are is helpful. And what's interesting in Colorado is that this was actually established by a Senate bill. And so we're really lucky that our, governmental officials in Colorado recognize the importance of this. And they directed the CWCB to assess the susceptibility of water resources, communities, and critical infrastructure to post-wildfire impacts, and to create a framework for communities to plan and implement mitigation strategies to minimize the impacts before wildfires occur. That's really it in a nutshell of what we're trying to do. Next slide, Natalie. And this is kind of similar to what Natalie was showing you before, but really, what we're talking about when we do these plans, even the statewide assessment, but even more so these kind of watershed-specific wildfire ready action plans, is we're looking for the intersection between hazards and values at risk. And the typical hazards that we evaluate as a part of a wildfire ready action plan and as a part of the statewide study that we did are hill slope erosion, mud and debris flows, degradation of water quality, riverine erosion and sedimentation, including fluvial hazard zones, and flooding. And typical values at risk that we're looking at how those hazards might affect, they include everything from ecosystems and, natural values, reservoirs and dams, water, infrastructure like municipal water intakes, agricultural intakes, obviously road crossings. I mean, anybody that's been out after a big debris flow happens knows how disastrous road crossings can be. And then, of course, life and property, everything from residences to hospitals to, you name it. And so really this is a figure though. And one of the things I like about this figure is that it was really created to be visually appealing and something that could be, digestible by the public, so that when engineers like myself are trying to explain this to an audience of a bunch of people from the Roaring Fork Valley near Aspen, we have some good graphics that can help to explain it instead of just a bunch of engineering terms. Next. This whole project really started with a statewide susceptibility analysis. I think it was probably about 3 years ago. And the state convened a group of experts led by Jeff Sickles with Ingenuity at the time. I was part of that expert panel as the expert on mud and debris flows. And, they had ecologists, they had geomorphologists, they had a lot of different people involved. And initially what the state wanted to do was to kind of do what Natalie was saying, which is figure out how these hazards relate to areas that are populated in the state. And so we really came up with methods to evaluate these hazards at a high level across the entire state of Colorado. And what this is really showing you here is just one of our maps that we created. This is really a map that combines a lot of the hazards and really shows the various susceptibility of values at risk to hazards, which is kind of what we're driving at. And so this map, even though it was done at a very coarse scale, really helps to guide the next step, which is to then go in and in these watersheds where you've identified at a high level that there could be hazards and susceptibility, to then go in and study those in more detail and figure out what you can do in terms of mitigation. Next. And again, this is more than just, doing one study and writing it up and publishing it. This is really trying to create a framework that, will be something that's a living living thing that communities can work with. When they create these wildfire ready action plans, for lack of a better term, they're like a master plan for the watershed for when a fire occurs. And the mitigation that these plans will lay out is not something that's going to be done in 6 months or necessarily even 2 years. These are long-term plans, and they will really need to be updated and changed over time as projects are completed and new projects are identified. So it really is key that this is a living framework and something that we can all work within to to increase our or decrease our risk when fires occur. Next slide, Natalie. So a number of the different types of mitigation projects that we look at, can be burn severity mitigation and fire prevention. In Colorado, we have a lot of community wildfire protection plans, and a lot of those plans will actually identify kind of the forestry management activities. And typically these RAPs, we oftentimes will have a consultant on there that can provide information on that, or perhaps fire behavior modeling. But a lot of times for the RAPs, we're very focused in on the water resources. But that's not to say that forest management isn't one of the most important parts of managing your post-fire risk, because it certainly is. It's just in Colorado, those are typically managed through a different process, which are the community wildfire protection plans. So we want our RAPs to be consistent with them. But, various types of projects, we really try to look at what can we do really with the natural systems. What can we do stabilizing areas within watersheds? Are there opportunities where we could restore wet meadows and allow areas for sedimentation? Alluvial fans are another opportunity for collecting sediment, and also, of course, managing places where you don't want to have development. Mulching and seeding obviously can be used in some areas, and they often are after fires. We really like the idea of combining ecological enhancements, for streams along with enhancements for post-fire resiliency. I mean, sometimes it's not completely protecting a value from the hazard, but it's allowing that value to recover more quickly and to be more resilient when it does experience the hazard. And of course, some of the projects we're really interested in are how can we, protect our reservoirs and our water intakes that communities rely upon? Is there a need for redundant storage? Do we need to have better management of sediment to, keep it from getting into the reservoirs to begin with? Or do we need forebasin reservoirs? There are a lot of different tools that we can use, and including emergency warning and non-structural or non-built practices like that. Next, Natalie. And so the primary objectives of a RAP, I wanted to kind of go over that. And, first and foremost, it's really to help communities understand which assets they have that are susceptible to post-fire hazards. Next. And then, once we know which assets are susceptible, we really work with the communities to help implement pre and post-fire hazard mitigation projects to lower that risk. And no matter how much pre-fire planning you do, there's always going to be some post-fire activities you have to take. But if you have a good post-fire plan, at least outlined and kind of fleshed out, then when a real fire happens, that's something that can be adapted much more easily and taken off the shelf and implemented instead of having to create it from scratch when you're in a hazardous situation. And then finally, we really want to develop standardized projects across the state, including hydrologic models, because these are obviously forecast models before a fire occurs. But as soon as a fire occurs, all you really need to do is switch out the assumed DNBR layer for your real DNBR layer, and then you actually have a real model of your fire with very little work that you need to do that can help you inform hazards from that specific fire. Next. And then the way that we really execute this is through a series of 6 tasks, and that begins with visioning and establishing goals and objectives. Stakeholder collaboration and outreach is critical. These are all watershed-based projects, so you have to get the stakeholders on board or you're never going to implement any projects. Task 3 is usually a very time-consuming one for the engineers, which is trying to pull all of the data together and filling in gaps in data sets. And then task 4, at least for me and Natalie, is some of the most fun analysis. That's really quantifying the hazards and identifying and modeling the hazards. And then when we have task 5, we really combine what we learned in task 4 about hazards with what we learned in task 3 about values at risk and assets, and we do the susceptibility analysis. And then once we've done all of that, we develop a pre-disaster mitigation plan and a post-disaster mitigation plan. And that's kind of an overview of the overall WRW process. Now, Wildfire Ready Action Plans are what we create through this WRW process. And what we're showing here are actually a number of different Wildfire Ready Action Plans that are going on in Colorado right now. Middle Colorado is one on the western slope that we worked on. That one is pretty much done. Roaring Fork River, that drains from Aspen to Glenwood Springs, and we're actually leading that RAP, working on a team with a number of people. Grand Mesa is another one on the west slope. Keep on going, Natalie. Upper Dolores River is another one draining into western Colorado. Next one. Along the Front Range of Colorado, we're working on a RAP right now related to water supply infrastructure for the city of Fort Collins and other partners in the headwater of the Poudre River. And then finally, Natalie, and I think this is the one she's going to show you an example on. Well, not finally, but Natalie's going to show you an example of one we've done in the Boulder and St. Vrain watersheds, which is actually where I live. And then finally, another one that we're involved with is down in Mancos, and that's one where we're a sub-consultant to another firm down there, and we're working on the burn severity and post-fire debris flows. So it's pretty amazing to think that in the space of about 5 years, maybe 4 years, I think, that this has really gone from a concept to something that's being implemented all across the state of Colorado. And, we've highlighted the ones we've worked on, but you can see that there are other ones. And when these are done, I think the state plans to go in and do some work to fill in this information and develop RAPs for areas that haven't been studied by watershed groups. Over to you, Natalie. Thank you.
Thanks. And one final comment on this map, it was the statewide susceptibility, that chloropleth map that Andrew was talking to with the greens and the reds. The state is using that map to say, okay, where do we have watershed groups applying for grant funding to develop these RAPs? And where do we have gaps where we don't have anyone that's developing a RAP, but we did see high hazard during the statewide susceptibility study? Okay, that's a gap area. And then the state, at least it's been a goal to go in and help fund a RAP to fill that gap. The point being, we want the HUC 8s, I think these are maybe HUC 8 levels, or these are HUC 12s. We want all HUC 12s that the statewide susceptibility study identified as high hazard, which is, it's high risk, so hazard, right, multiplied by susceptibility. There should be a RAP for all of those areas. And Right Water, we were part of the technical assistance team for the state. So working on what is the framework that should go into a Wildfire Ready Action Plan. We helped author the template scope of work that a consultant has to follow when they're developing a RAP. And then as Andrew just mentioned, we've won several competitive bids for actually developing those RAPs. So it's been really nice to be with the program from all sides, both from a consulting and from an advisory role. So the rest of this presentation is going to be pretty rapid fire, and we are going to show you example components of different Wildfire Ready Action Plans to illustrate for you exactly what's going into the RAPs. What are we specifically doing for hazard analyses? How do we get around the fact that this is being done in a pre-fire context versus post-fire when we have certainty on burn severity outcomes, for example? So I'm going to jump around the state a little bit as I illustrate for you what goes into RAPs. So the Boulder study area, this is the Boulder headwaters. And this includes the St. Vrain watersheds. This is in the Front Range of Colorado, kind of between Denver and Fort Collins. And this is a RAP that Right Water has been a sub-consultant to another consultant that primed this RAP. It's a huge study area. These black polygons are HUC 12s. So this has about 40, maybe 35 HUC 12s in the study area. And that has presented some major engineering obstacles. We are being asked to model in detail the hydrology for study areas that require a lot of computational time and input. So it's been fun from a programmatic perspective to figure out how can you guide consultants to detail and sufficient resolution to actually get some meaningful information from these modeling exercises without blowing budgets. These are grant funded, their budget and time constraints are real. So the Boulder study area, again, about 38, 40 HUC 12s. And as an example of task 3, this data collection research gap analysis, what Andrew was talking about there is the collection of values at risk data. So when we are first hired by, let's say, a watershed group, the Watershed Collective is our client for the Boulder RAP. We have to work with our client, the watershed group, or maybe it's a municipality, and all of their stakeholders to get their geospatial data. Where are your water intakes? Where are your reservoirs and dams? Where are your utility lines? And some of those data are publicly available. So we do have a data set assembled for the state of Colorado with some national data sets in there to try to cover most of the bases for the values at risk type of data that a RAP is supposed to be evaluating. And then we go into stakeholder groups and say, all right, do you have private data that you also want us to be evaluating with this Wildfire Ready Action Plan? Maybe it's, again, a utility that doesn't want to publish where all of their substations are or transformers. Well, we will include their data as a private data set in our susceptibility analysis and then not publish it in the final VAR data group. But these are the data categories that we are supposed to be evaluating their susceptibility to hazards to. And I just wanted to show you an example. This is before we started cleaning data, but for that Boulder study area that I showed you, man, we got so much data, and it really takes some intentional, careful effort to go through and figure out where are we missing data. You know, we have Colorado specific data sets from CDPHE, that's the Colorado Department of Public Health and Environment. They provide big data sets on where are diversions and canals, but that data set isn't necessarily comprehensive. So you have to use your engineering best judgment to really start understanding your study area and identifying gaps, and then going and finding data to fill those gaps. And eventually you want to collapse these messy consortium of data down into a meaningful data set for your client that can actually be, again, inserted into the susceptibility analysis. So this is another example of, this is the headwaters of the Cache-la-Poudre River where we're doing a RAP. And I just wanted to show you what a cleaned data set would look like. This took a lot of effort to get down to a single geodatabase of layers that does not have redundant inputs. For example, reservoirs. We had like 10 different layers with reservoirs highlighted in the layer, and we wanted to collapse that down so that you'll only have a reservoir represented once. And we can then hand this off again to our client and as a really nice compiled final data set for the susceptibility analysis. Let's move on to task 4, the post-fire hazard analysis. And this really should be analyses because there are several different analyses that need to be incorporated into a RAP. So from a high level, these are the hazards that we are required to evaluate with Wildfire Ready Action Plans on the top row. And then I'm going to talk briefly about our evaluation approach for how we model each hazard. So the hydrologic hazards that we have to evaluate: increased runoff, flooding, hill slope erosion, mud and debris flow, and geomorphic hazards. For increased runoff and flooding, I'm going to talk about that first. The tools that we're using to evaluate hydrologic modeling are, physically based modeling. We're using HEC-HMS, distributed, not typically rain on grid, but we do want to get detailed information, for example, hydrographs at certain design points that requires some detailed modeling. You can't just be using stream stats to evaluate changes in peak hydrology pre and post fire. We really want enough information for engineers to be able to understand, okay, what's changing in a post-fire environment in terms of flow, magnitudes, and timing, such that we need to, for example, maybe change the design of a bridge to accommodate increased flows and typically bulked. So the output for hydrologic modeling would be pre and post-fire flows for a range of design storms, with an objective of comparing post-fire flow to existing capacity of downstream stream crossings, channels, et cetera. And it's really the objectives of each of these models that drives the tools that are allowable to use for a RAP. And Wrightwater was part of the team that authored guidance on what needs to be included in your hydrologic modeling effort for RAPs. For flooding, no surprise, hydraulic modeling is required. For example, you can use HEC-RAS, typically two-dimensional HEC-RAS modeling. And we're getting short on time. But the point is here to understand changes in inundation footprints and stream power in a post-fire environment. So one example of the effort that went into modeling hydrology in a RAP, this is again a rapid fire slide, but I just want you to kind of get your hands around how much work is required for these huge study areas that include 40 HUC 12s. For the Boulder hydrology study, we used 5 different existing HEC HMS models that were calibrated to a huge flood. This is a record-setting flood that occurred in Colorado in September 2013. I bet some of you even studied that flood up in Idaho. And we merged all of these models into one updated HEC HMS model. So that was a nice data product for a client. They now have one model that's, there's 2 major water bodies that are eventually feeding into the South Platte River down here at the outlet. And it was a pretty good exercise in bringing together models with varying spatial resolutions and different initial calibration objectives and merging that into one model. So I think this final model has somewhere around 300 subbasins in it. And Andrew mentioned the Roaring Fork RAP that Wright Water's leading. The Roaring Fork is just in about the middle of our state. It's where Aspen is that some of you may have skied at. That is a 1,400 square mile study area. And I think we have 1,800 subbasins in our HEC HMS model. So that's been quite a modeling exercise. I mentioned that we helped author the guidance for conducting pre and post-fire hydrologic hazard evaluations for RAPs. All of the materials for the Wildfire Ready Watersheds program are available online at this web address. So this is a nice about 20-page document that outlines in pretty good detail. This is exactly how you need to parameterizing with some wiggle room your hydrologic models and what you should be using for calibration, et cetera. So that's a really nice place to start if you're considering what to include in your model criteria. As far as hill slope erosion goes, we are allowing statistically based models. Just because sediment transport modeling and sediment yield is such a complex science, and we don't have time to do detailed transport modeling for all of these RAPs. So we've allowed revised universal soil loss equation type modeling to be conducted and doing something to look at sediment delivery ratio on top of your gridded output for Russell. And I'm just going to keep going. For hill slope erosion modeling, this is an example of what we used for the Boulder RAP again. We actually used some Russell-based modeling that was conducted by an outfit out of CSU, the CFRI, Colorado Forest Restoration Institute. They had already developed Russell modeling. So Russell is average annual erosion post-fire. You can look at it post-fire if you change your sea cover factor appropriately. And what we did is took this gridded output already, and we summarized results at the level of subbasins that we were modeling debris flow activity in. So we have a nice data product where we're looking at predicted post-fire hill slope erosion at a subbasin level. For mud and debris flow, we're also allowing statistically based modeling. This is the USGS M1 model. This is the model that the USGS deploys after wildfire activity in the Western United States. And anyone can look at the output from the landslide hazard group and see what USGS is predicting in terms of debris flow, probability likelihoods, and volume. So this is just the same regression type modeling that we're applying in a pre-fire context. And that model is based on a paper, it was actually Sukan in 2010, but the most recent model coefficients were published by Dennis Daly in 2016. You're probably familiar with the input variables to this model. Again, it's a regression-based model where we're looking at the proportion of upslope area burned at higher moderate severity. You have to have steep area above 23 degrees. We're looking at rainfall accumulation, DMBR, like Andrew mentioned, and that's where your fire effects on soil hydraulic properties and vegetation comes in, and then soil erodibility. So one of the hardest parts of RAPs is the fact that we were looking at post-fire risk before a fire occurs. So we have to have some estimate of how burn severity may play out under certain fire weather conditions. What we've decided is to infer burn severity class from crown fire activity output layers from fire behavior models. So for the statewide study, at least, we used a crown fire activity output layer from a FLAM map model, and FLAM map was created by your neighbors over in Missoula, Montana, the USDA Forest Service Fire Science Center. It was Mark Finney that published this FLAM map model originally. So that FLAM map model can be parameterized to look at really extreme fire weather conditions, 90 or 97th percentile for fuel moisture, wind speed and direction, et cetera. So what happens if kind of the worst case scenario plays out on the ground if you have an ignition source? The resultant crown fire activity class can have, we just directly convert these different classes, for example, surface fire activity to low severity. And then we do some work to actually recalibrate the resultant burn severity classes to a continuous DMBR scale using local burn scars only. The other model input variables for debris flow are, no surprise, we have DEMs. We use NOAA Atlas 14 for rainfall accumulation for 15-minute durations. You can use your DEM to get slope, or you can use the landfire slope raster. And then just the NRCS, GNATSCO, or SERGO soils data. We have a nice basin delineation model for our debris flow model that Wrightwater built to delineate subbasins. And then you run those regression equations on each subbasin to determine debris flow occurrence likelihood. So this is an example output from the debris flow modeling exercise. We are looking at or predicting the debris flow probability from a 1-year recurrence interval storm. Darker red basins mean you have a higher probability of a debris flow with a 1-year peak 15-minute intensity rainfall. And we've grayed out any subbasins that have less than 6-degree slopes, because you can have pretty high debris flow likelihoods with high rainfall accumulations, even in, pretty low profile slopes. So we just take out subbasins that are not steep enough to really have true physical debris flow risk. And I'm just going to keep going because of time. You can combine debris flow likelihood and volumes to understand a combined hazard categorization. So we do that for our debris flow likelihood. And then to understand debris flow runout zones, we've been using a USGS model called the Griffin model. I'm not sure if anyone here is familiar with Griffin. I think it's a pretty new model. And that is also statistically based, but Griffin stands for growth, flow, and inundation. And essentially, you can model the source and transport zones in a DEM for where material will originate and source from as material moves down your watershed. And then Griffin will also model where deposition zones are. So this is nice. We've been able to write some algorithms to translate our predicted debris flow volumes for a given storm interval back onto these Griffin modeled inundation polygons to understand where the actual debris flow risk exists on the landscape, even though the initial model is just a statistical model. And then geomorphic hazards. The fluvial hazard zone mapping is part of the assessment to understand where risks associated from degradation and aggregation of sediment exist in an active stream corridor. Right, so we have debris flow erosion modeling and sediment yield modeling, which is really looking at hill slope erosion modeling, but we're still not doing a great job of getting out in the field and understanding exactly where the material that is generated from burned watersheds is going to pose problems in your active stream corridor. So the fluvial hazard zone mapping portion of a RAP is really based on Colorado's FHZ protocol. Over the last probably 7 years, Colorado's put a lot of effort into defining and building a program to map fluvial hazard zones around our state. So we're following a protocol that's been developed really for a higher purpose above just post-fire. And the objective of fluvial hazard zone mapping for RAPs is to understand, again, where in-channel geomorphic hazards are likely aggradational and depositional. So for hydraulics, it's really FHZ modeling for a RAP. You are hiring a geomorphologist to perform a desktop exercise that's field validated, where that geomorphologist is looking at aerial images, other indicators on the landscape, where is the actual active stream corridor? Where is that stream moving around between its valley confinements? And they map the active stream corridor and then a fluvial hazard zone with a buffer. I just wanted to bring up one quote from the Colorado Fluvial Hazard Zone program. The FHZ is the area a stream has occupied in recent history, may occupy, or may physically influence as it stores and transports water, sediment, and debris. So by having an actual mapping in a shape file, we'll do an intersection with assets and understand, okay, is this important diversion structure that might be the primary water supply for a municipality? Is that in, it might not be in the stream corridor right now, but has it been in the active stream corridor anytime in the recent history that matters for geology, and therefore could it be in danger in the future? That's what we pick up with FHZ. So going back again to the Boulder RAP that was developed, again, this is just north of Denver, south of Fort Collins. The pink lines are where fluvial hazard zones were mapped for our Boulder RAP in 2024. There was already some FHZ mapping that was pre-existing. And then the geomorphologist also mapped existing active stream corridors. All right, about 12:10. So the last thing I want to mention is susceptibility. What we do with susceptibility is we actually do some cool workflows in GIS to overlap the hazard and inundation layers from the pre-fire hazard modeling that I just discussed with the values at risk data. And we start ranking, okay, what are our most important VARs for the community that we're developing this RAP for? And which of those VARs are vulnerable to the frequency and magnitude of events that we've explicitly modeled with the hazard analyses. So that's the output of susceptibility. This is the workflow. Maybe you'll get a copy of these slides so you can examine that workflow if you'd want yourself. And then, as Andrew mentioned, the whole point of this is to use the results of the susceptibility analysis to inform selection of hazard mitigation projects. Where do we have really high debris flow risk with a community right at the mouth of a steep drainage? If that's the case, hey, let's prescribe some proactive weather monitoring so that we can get rainfall trigger warnings out from the National Weather Service. Where is gully stabilization important? Because we have because we have high erosion risk. Are there some bridges that can't be removed because we have important access points, but we know that the bridge is not large enough to capacitate both flows in a post-fire debris flow type regime, right? Let's upsize that bridge crossing. So the whole point of this is those hazard mitigation projects that are prescribed by a RAP. Andrew, I will pass it along to you for resources for additional information.
Thanks, Natalie. And I'll kind of wrap this up quickly because I know this ends at 12:20, and Natalie and I can certainly hang on if people have questions to ask. But I wanted to share just a few slides with some additional resources for information. And I will make a PDF of this and send this slide deck to Tim. So if folks want it, he can distribute it or post it for the group. But we have a whole lot of fact sheets that we've developed, and Natalie and I helped develop a number of these. We had some of our other team members that developed other ones, but this is really a wealth of information that includes information for people, agencies, or watershed groups that are planning RAPs, but also for the people conducting them. And this is just a list. Next slide. And this is actually a screenshot from the state's webpage that is where that hosts these fact sheets, and you can see that they kind of organize them. They have guidance for the sponsors. They have a typical scope of work that you can have, and a lot of other things about getting prepared. They also have guidance for the technical teams that are working on the RAPs related to the various topics Natalie and I have discussed today, and that's just a few of them. On to the next slide. And here are quite a few of the other ones. So there are actually fact sheets on a lot of hazards and hazard mitigation for different categories, as well as a template scope of work for an early warning system. Next slide. This is just an example of one of the fact sheets. This was the post-fire debris flow fact sheet that we worked on. And we've really tried to write these in such a way that, the people that are creating these RAPs should be using these documents for guidance on how to execute what they're doing. And we find that these are really important for ensuring that we have some sort of comparability from one study to the next, and that, that we're going to be able to use these in a statewide level, which is the ultimate goal next. This is actually the webpage for Wildfire Ready Watersheds. I believe that QR code still works. I gave it a try when I was putting this slide together, and it pulled up the website. So if you're interested in more information, this is an excellent website to visit. Next slide. And with that, we really appreciate you attending the presentation. We'd be glad to answer any questions you have. And, if any people on this webinar have interest in trying to start a similar program in Idaho or whatever state you may be through, and you're interested in learning more about this, feel free to reach out to Natalie and I, and we'll be glad to talk to you, but we'll also be glad to put you in touch with folks at the state of Colorado, or other partners that are on our team if you have questions that they could help answer, because we really think this is a neat program. It has a lot of potential to protect people, to reduce damages following wildfires, and give communities a peace of mind. And we really hope that this is something that everybody in the Western U.S. is doing in 10 years from now. So thank you for the time. And Tim, thank you so much for the invitation to present to this group.
Yeah, thanks, Natalie and Andrew. And so if folks have questions, I would encourage you just to either just jump in with audio, or if you want to type something in the chat, I'll just keep an eye on the chat. And I recommend too for Andrew and Natalie just to watch the chat.
Hi, yes. I have a question.
Yeah, go ahead.
My name is Rebecca Garino, and I'm at ISU. In the map that you showed of high-risk areas, some watersheds had RAPs, while others that also appeared vulnerable did not. It's where, like, you guys had your circles amongst your part projects. You mentioned pursuing grant funding to expand coverage. Given that many grant programs are currently facing reductions, I was kind of curious, how realistic is it that these high-need areas will actually receive funding and support for RAP development?
I'd be glad to take a first shot at that, and then Natalie, you can chime in. I think one thing that we're really lucky about with the program we have in Colorado is that it is state funded, not federally funded. So this is funding that our state has realized that we have a big problem with fires and post-fire damages, and that they're, every dollar they spend on a preventive program like this is saving them losses in the future. So I think that it's a little more resilient because of the fact that we do have state funding. But it's going to take time. And, we've made a lot of progress in 3 or 4 years. But, we're in this for the long haul, and it may, take another 5 years to really fill in the gaps, or maybe even longer than that. But I think if we do it in a prioritized fashion, we really will see the benefits of it. And as we see the benefits of it, we'll see more openness to funding additional studies, we're hoping. So.
Yeah, thanks, Andrew. I agree with everything Andrew just said, and I'll add just a couple more details here. One of the goals for the state when they developed this program was capacity building. Let's make sure we get a bunch of consultants that know how to do this modeling, that know how to fine tune curve numbers, et cetera. But there's still kind of a learning curve when you hire a new consultant to put a RAP together. And Sarah, the state has set aside some additional funding. It's probably been allocated at this point, but to hire the TA team, this technical assistance team that's done so many RAPs, that was part of developing the framework, that we can go in and do some of those post-fire analyses for a lot cheaper than it takes to develop a whole RAP for some of these, red areas that don't have a RAP yet. We've developed workflows that automate a lot of what used to be a more manual process. So I think that's how the state is going to get around some of these gap areas, where maybe there's not even enough urgency among the local watershed groups to ask for grant funding themselves. Great question.
Wonderful. Thank you, guys.
Hi, Anna here. I was just wondering, you talked about how this is a living document, essentially, that these RAPs are not just kind of like a stagnant thing. How often do you anticipate having to check in on your previous models to update susceptibility and risk in these watersheds?
Anna, that's a great question. And I don't think we've gotten far enough into the process yet to really kind of know for sure what that time frame is. I mean, I think it depends on a few different things. And, typically in urban areas, we do storm drainage master planning in Colorado on the Front Range. We've been doing it for decades. And those master plans are usually updated every 10 to 20 years because oftentimes there's been enough development in the watershed to necessitate it, or just changes in methods. But I tend to think that these, it's really going to be not so much changing the models. Because I think that the models will remain the same. It's more new bars getting built. And, we hope that hopefully some of this will be used by local governments to avoid building in really hazardous places. But, nonetheless, projects are going to get completed, and there will be new projects and changes in priorities. And so I don't know, I think about every 10 years is probably 10 to 20 years is about what I would see for needing to go back in and look again. The local watershed groups that will kind of own these wraps can certainly make, more frequent updates, and perhaps save the need for a comprehensive update by just making little updates as they go along. I hope that
Yeah,
answers.
two things to add to that. First, Anna, another really valuable question. I think that because the values the VAR data themselves, those are going to shimmer over time. A house is over here, it may be rebuilt, and a community may be over there. So having the watershed groups have access to the hazard layers themselves, so that a homeowner can go in and look at, well, where is my house relative to the hazard layer? You don't have to have the actual GIS intersection with the ranking to understand, oh, I know on a map my house is located right here, and this is the likelihood that a debris flow will occur with the 1-year storm or whatever it is. That kind of takes away the overfit nature of the susceptibility analysis being conducted on where the physical structures exist in the landscape today. And then the other thing that wobbles over time truly is fire risk, though, right? I mean, let's say you have a burn scar, you have the Cameron Peak fire. That was a fire that consumed half of our study area for this wrap up here, number 9. So we've developed some nice workflows to update the burn severity projections based on vegetation recovery after a fire, or even the presence of a fire to consume some of that potential fuel source. So that also should drive some reanalysis of likelihoods and magnitudes of post-fire hazards. And I think it's gonna be up to the owner of the wrap for how often they can fund an update.
Awesome, thank you.
I'll jump in. I don't know if you guys are seeing, there's 2 questions, 2 really good ones that came in the chat.
Yeah,
Sorry.
but Natalie, that one from Brittany looks like it's got your name written all over it.
Advice would you give students who are interested in pursuing careers? What about those with a GIS background? Yeah, that's a great question. Pun intended, fire is a pretty hot topic right now. I am always perusing Google Scholar to see what new fire publications are out there. If you live in the Western United States, it's really likely that if you're a student, there's someone at your university doing some pretty cutting edge fire modeling of some type. I think the question you have to ask yourself is, where is your interest? Is it in the acute fire event itself? Are you a forestry student that wants to help prescribe where fuel treatment should occur to manage severe fire activity in the first place? Or are you really interested in the more engineering heavy post-fire landscape of hydrology? Where are there flash floods? Where is there water quality degradation? I find that there's often conflation between the two. We are a water resources engineering firm, so we should not be doing fire behavior modeling. We're not foresters. So if you're a student, really ask yourself, where is your interest in the fire reaction chain? Right? Figure out where you want your topical expertise to be. And if it is in the hydrology kind of segment of it, the post-fire, it took me a long time to understand this. I had a master's from an environmental science program that was focused on watershed mechanics. It's not environmental science students that are doing hydrology and hydraulic modeling. It's really engineers, because there is a duty of service for understanding fluid mechanics, et cetera. So making sure that you have if you really want to be the one pushing the buttons, and Andrew may disagree, but ensuring that you have enough of the fundamental engineering background to be qualified to be doing that type of modeling, I think is pretty important. And then GIS background, So important. All of this, we have geospatial workflows, sometimes just in Model Builder, oftentimes in Python, that we have running behind all of this stuff. AI has certainly changed the landscape in your capability to do geospatial modeling without being an expert, but you darn well better need to know how GIS works and not just building maps, right? But actual geospatial analysis if you're going to be doing anything with large data sets. So take your GIS classes. You know, if you can have a Python class in there too, that'd be really, really helpful. I suck at Python. I'm pretty good at R. So I kind of go back and forth between GIS and R, and I find that to be a pretty productive way. That's my input.
I think that's great advice. Yeah, start with the building blocks. I didn't take classes on this in college. I was in Virginia. They don't have too many problems with post-fire hydrologic hazards. And this is something, you know, but I had the skills with hydrology, fluid mechanics, hydraulics, and sediment. And if you know those things and have those skills, you can put them together to learn this very easily. The other thing I'd say is if you do get an opportunity, go out and visit a burn scar. Go out and visit one that's fairly fresh. You probably have to be accompanied for safety issues, and then go out and visit one that's a little bit older and, you know, start to really understand how a watershed responds to a fire, and seeing it on the ground is really the very best way to do that and understand it.
Yeah, that's something that we and every other firm out there is going to struggle with is, do we hire the data science expert that can code things up? Do we hire the awesome engineer that knows fluid mechanics like the back of their hand? Really, we need someone that's pretty well versed in both. But as a rule of thumb, we are not going to hire a data scientist that doesn't have a background in the fundamental science and engineering that we're responsible for. So I think not losing sight of that. It's tough to wear multiple hats. Use the tools that you have available to you as a crutch, right? To be a better engineer or coder or whatever it is. But make sure that you're taking the classes to be a subject matter expert in hydrology, if that's where your interest is. And then lastly, there's a question from Kim Roosh. Did you have to demonstrate the financial impact to economic growth of fire impact to the Colorado legislature to get funding, and how RAPs can better prepare communities to get back on their feet after fire? Do you have a sense for that, Andrew? What was justified?
I don't think that there was specific economic analysis for it, but I do think that when it was approved, it really came on the heels of a number of very disruptive fires that affected, you know, some major areas in the state, including a couple of big ones up near Rocky Mountain National Park and Fort Collins. One of the ones near Fort Collins killed a few people in a debris flow after the fire. And, you know, what I can tell you is that since the early 2000s, this has been a fact of life in Colorado more years than it's not. And so I think that really the economic impact was evident to the legislature without needing much proof, because we've been living it lately, and they've been, you know, granting money to communities for disaster relief. So so I don't think there was really a specific economic analysis that I'm aware of. I think the grant program started out maybe as like a $10 million kind of grant, and that has been renewed, I understand. But that's really $10 million. You know, when you look at all the dots and watersheds Natalie's showing on here, is not a lot of money for studying all of these areas. And so that money has actually been going a long ways. And, you know, and it's, again, a great that our state of Colorado is supporting this. And I do think in the long run, it's really going to serve our communities here very well and help to protect the public. So.
Yeah, that 2020 fire year that Andrew just mentioned, that set records in our state for largest area burned. It was the first time a fire jumped over the Continental Divide, the East Troublesome Fire, and threatened the town of Estes, way up, way high elevation, pretty cold up there year round. Crazy to get fires jumping over from, you know, one side of the watershed divide from the country to the other side. So
talking about economic impact, Estes Park is where Rocky Mountain National Park is, which is a huge tourism engine in that part of the state. So, you know, that that was an amazing fire, though. Well, thank you all. We really do appreciate all the people that took time to attend today. And Tim, thank you so much for organizing this. Really appreciate all the great support that you and the folks that work with you have provided in getting us prepared for this.
Yeah, thanks, Andrew, and thanks, Natalie. Really appreciate you taking the time. And hopefully we'll see something like this in Idaho sometime soon.
Well, have a good trip, Tim.
All righty, thanks, everybody.
Thanks for everyone's attention. Take care.
And
Right,
then
bye-bye.
could I ask you one more question?
Go for it.
Yeah.
Yeah, sorry, I'm here in Boise. I spent some time in like Tennessee, North Carolina area this spring and was just seeing like some of the impacts from the hurricane that happened last fall and was thinking about like if this framework you think could be applied to other natural disasters like hurricanes and such, and if there's like any major challenges to doing something like that.
Yeah, that's a great question. Yes, absolutely. The fundamental framework could be applied. It's where are your data and where are your hazards. Some of the modeling workflows would definitely have to change. You know, we don't have, even though the basis of this M1 USGS model that we apply for debris flow risk, you know, is rooted in mass wasting activity, which is landslides. This USGS regression equation is fit to runoff initiated debris flow activity in a post-fire setting. So there'd have to be some work to figure out what are the correct models to be applying in whatever the scenario is. Is it seismic? Is it hurricane where it's severe winds and storm surge? But I think that this framework sets a really nice roadmap for what is the scope of work that needs to be included to actually get something that provides projects that are addressable on the ground.
You know, and I think FEMA has historically provided some of that, you know, perhaps not all that we need, but with regulatory floodplain mapping, flood insurance studies and things, many areas do have mapping. But the problem is that sometimes it's not that accurate. It ends at the 100-year event, which we know that flood damages don't end at the 100-year event. They only increase when you get above it. You know, there's some 500-year mapping, but frankly, nobody pays attention to it when they're building. And there's no modeling of sediment or debris blockage typically. So, you know, I think there are things that could really be improved within the framework that we have. One of the things that some people are starting to do with flooding that I think is really kind of neat is called the 1% plus floodplain. So, you know, if you go in and you do statistical gauge analysis of a stream gauge, the 1% event, of course, is your 100-year flood event. Well, the 1% plus event is that event, the upper confidence limit or the upper 60, the upper one standard deviation above that level, I'm sorry, is what I mean by the upper, is what the 1% flow is. And I did a study in Colorado where we figured out how to use modeling results to come up with those. And typically, you know, that'll map out a floodplain that's somewhere between a 200 and a 500-year floodplain in terms of return periods. But it gives people this idea that there's this zone outside of the 100-year that's kind of uncertain, right? The 100-year might be here or it might be out here. And part of the problems we've had with the messaging from FEMA is that you're either on one side of the line or the other. And we know that floods aren't like that. So anyway, I could talk about FEMA. I mean, I do a lot of FEMA work, so I could obviously talk about this for hours. And if you're interested in talking more, just let me know, but I won't keep on rambling here.
All right,
Good
yeah, good question. All right, I've got a hard stop, so I have to run, so sorry to have to shut it down. But again, it was great having everybody today.
And for the students out there, keep up your good work. You know, we're relying on you to come fill the positions that are opening as people move up. So keep up your good work. Reach out if you have mentorship questions. You know, we've worked in consulting for a while and have some thoughts there. Thank you.
Super, thank you.
Thanks, everyone. Bye-bye.
All right, cheers.